So in this lesson, we are going to explore math functions in C programming. These are built-in functions provided by the math library that help us perform common mathematical operations like square roots, powers, logarithms, trigonometric functions, and many more. So by the end of this lesson, you will know how to use them and when to use them. So let us get started. So in C, most math functions are available in the math.h header file. So to use them, you must include that header file, that library. Okay. So also when compiling in some environment like GCC, okay, you may need to link the math library, okay, using the flag, okay, and the flag is like this, but I'm not going to show it to you, but what I'm going to show you to you how you can run it. Okay, it is going to run. Okay, you can link it like that using that flag, but don't mind about this one. Just know you can use that one. Okay, so if you get errors that I'm not going to get in this video, just know you are missing out like that one. Okay, so let me show you. So in order to use these math functions, we are going to include, we are going to use the hashtag include preprocessor directive, and then we include the math.h, okay, .h header file like that. So after doing that, we are going to see the common ones, okay, the common one that we have. Okay, so the first one is the square root, okay, the sqrt, which stands for square root. Okay, so we have sqrt, as you can see, sqrt, that one, sqrt, and it is a function. So to call a function, we need to provide those parentheses like that. Then inside here, as you can see, it takes in a double. Okay, so you can provide in an int. Okay, so for example, if I provide like 16, so the square root of 16 is known. So okay, so we are going to get like, we are going to get 4. Okay, so if we do this, that we get integer, but remember it is going to return a double. Okay, so if here we are going to have a double, or Control Z, so this one is going to be a double, and the double, let us name it X, and we are going to get it like that. So after doing that, let us now try to print something. Okay, so let us print. So here we are printing doubles, so let us use that one instead. Remember, instead of a double, but I think we are going to print out, instead of a double, let us print out a float. Okay, so X like that. So instead of a double here, let us, instead of let us do that. So if we save and then we open our terminal, so I'm using PowerShell for compilation. So if I press GCC and I run my program like that, as you can see, we get this output. Okay, we get this output. So even if you put here, let us put here int, and here we change to d, %d, then we try, let us try that one and we see. Let us try that one, GCC. After that, as you can see, we get an integer instead of a float. Okay, point number. Okay, like that. Okay, so we have another one which is the power. Okay, POW. Okay, power. Okay, and this one, it looks like this. Let me show it to you. So we use it like this, power, that one. Okay, power, and this one, the power returns so if we have power like that, x and y, and this one is going to return the x, okay, raised to the power of y. Okay, like that. So for instance, if we have let us have 2 and 3 like that, so it is going to return 2 power 3, okay, like that, which we know that it is 8. So if we save and then we run, we compile, then we run, as you can see, we get 8 out. Okay, so we can also change it to float. Okay, we can change it to float, but we get that one out. Okay, if we are using an integer. Okay, so another one, we have what we call the cube root. Okay, CBRT, not key, CBRT. So it looks like this. So the CBRT, cube root, like that, cube root. Okay, and this one is going to return the cube root of the number that we provide in. So here I'm going to provide in like 4. Let me provide in 4. So if I provide in 4, we know that the cube root, let us look at the cube root of 4 and we see. So if we do that, we get 1, no, 1, yeah, y1. Okay, so let us try to the one that we know, okay, very well. So we know that, let us try to get the cube root of 27. instead of 3, 27, okay, because we know that 3 power 3, okay, we are going to get 27. So if we do that and then compile and then we run, as you can see we get 3 out, okay, because 3 power 3 we get 27, and 27, the cube root of 27, the cube root of 27 we are going to get 3, okay, for those who know math, basic math, okay. So let us now take a look at trigonometric functions, okay. For example, sine, cosine and tan, okay, and these ones they expect the angle in radians, okay, not degrees, guys, not in degrees, okay. So for instance, if we have let us have something like, let us provide here, let me show you how we can use it. So here we use the sine like that, okay, we call the sine like that, and we take in the number, okay, radians. So for example, we have pi, which is 1 or 3.14159 blah blah, okay, like that. So by 2, okay, pi over 2, okay, pi over 2, which is in radians, okay, which is in radians. And if we save and then we try to run our code, compile and then we run, we're going to get out here, we have got out a 0, okay. So here we have got out a 0, okay, like that. So let us try for pi 3, like that, we see if we will get a different answer. So guys, we still get a 0, we get a 0. So here, instead of using this one, let us use a float, okay. Let us change to a float, and here let us have a float. If we save and then we go back to 2, like that, and then we try to compile, then we get, and then we run, as you can see we get 1 out, okay, 1.0 something, okay, we get 1 out, okay. So which means that float is somehow better, okay, because with int we are going to generate some errors, okay. So but for this one we get that one out. But let us try 3. Remember the other time we got zeros, okay, when we used the 2 and the 3, okay. So let us try to use 3 and we see if we will get the same answer. As you can see, it is different, okay, it is different, so we get that one, okay. So get that one. So we have also what we call the inverse trigonometric functions, okay. We have, you can do the same using sine, cosine and tan, okay. So with the inverse trigonometric functions, we have a sine, a cos, we have a tan, we have a tan 2 and something. So let us take a look at example, which is the a tan, okay. A tan, these ones are advanced. For example, we have a tan, let us use a tan 2, a tan 1. Let us use a tan, then this a tan let us provide in 1, okay, which is going to give us which is the same as pi over 4, okay. So this one is the same as pi over 4. So if we save and then we compile, it is going to give us, I think, 0.7 something, okay. Yeah, we get 0.78 something like that, okay, because pi over 4 it is equals to that one, okay. So let us now take a look at exponential and logarithmic functions, okay. For example, the log 10 and even the exponential, okay, the exponential function, the exp function, okay. For instance, we can have here, let us have this one, instead of, let us make all of them to be floats, okay. So here we can use the exponential by just doing that one, so x, and then here we can provide a number, okay. For example, if we, for this one, the exp, this one is going to return the raised it is going to return e, okay, e, you know, e, okay, e raised to power 1, okay, e, you know, e, okay. You can find it on your calculators, on your scientific calculators. So if we save, I think e to power 1 is, it is somehow, it is 2.7 something, okay. So if we save and then we try to compile and then we run, as you can see we get 2.7, okay, 2.7 18282, like that, okay, because e to power 1 equals to that one, okay. So for instance, we can also use the log, okay, log is also there. We can use log, and the log, this one is like, it is the natural logarithmic, okay, logarithm, okay, or you can call it logarithmic. It is the natural logarithm. Okay, so let us natural logarithm, then let us provide in the natural log of natural logarithmic of let us provide 1 point 2 point something like that. Let us provide a float point number, okay, like that, which I think it must be around it will be around 1. Yeah, I think so. Let us try. I don't know the exact answer, but let us try. Oh, we get 0.999, okay, which is approximately 1. Okay, so we get that one. So we can use it like that. We can also use another one for mathematicians. You know how these you can handle these ones. I'm not a mathematician. We can also use the log 10 and this one. Okay, what I know is it is the logarithm base 10. Okay, this one I know it very well, logarithm base 10. And here we can provide, for example, 100. Okay, you know it very well. So for 100 we are going to get 2. Okay, so this one, the log base 10. Okay, or the log of log base 10, then 100. Okay, we're going to return 2. Okay, so if we try to run to compare and then we run, we're going to get 2. Okay, because it is a float, then we are getting these extra zeros. Okay, but we get 2. The answer is 2. Okay, so we have others. Okay, we have other functions found in the math library, which include the rounding functions. Okay, these ones include the ceil. Okay, the ceil, and this one rounds up to the nearest integer. Okay, so for example, if we want to round off something here, let us try to remove this one, and then we get, let us use ceil like this. So as you can see, we have ceil, and let us round off 2.3. okay, let's round off 2.3 with ceil like that, and then so it rounds off to the nearest integer. As you can see, we get this one. Okay, which means we have rounded off to the nearest integer. Okay, so let us see how we can use another one. Okay, which is called the float. Is the opposite of ceil. Okay, and this one rounds it down. Okay, this one rounds up. Okay, the ceil rounds up to the nearest integer. Okay, but the flow, we have the flow. Okay, so let us provide, so the flow rounds down to the nearest integer. Okay, so let us use flow here like that. If we save, then we try to run, compile, and then we run. As you can see, we get 2. Okay, it rounds down, okay, to the nearest integer. Okay, so let us take a look at another one, which is called the round. Okay, and this one rounds to the nearest integer. Okay, no more rounding. Okay, so it is here, round. As you can see, if we do that and then we compile, then we run, as you can see, we get 2. It is normal. So if we have here 0.5, save, and then we'll try to compile, and then we'll try to run, we get 3, as you can see. Okay, it is a normal round. Okay, we have also another one which is called the trunk, and this one removes the small part. Okay, it's called the like truncate. Okay, remove that extra part. Okay, so for instance, we can use it like this. Let us use trunk. Where are you, trunk? So if we do that, then we'll try to compile, and then we'll run, we get 2. Okay, so it just removes that the small part. Okay, so even if it is 9, okay, so you might think that it just rounds off, but it tracks out. Okay, it removes that around. Okay, as you can see, that decimal part. Okay, as you can see. So we also have another categories of functions which are called the absolute value functions. Okay, Okay, for example, we have the fabs. Okay, fabs, and this one returns absolute value of a floating number. Okay, so let us take a look at an example here. So here we have fabs. Let us have, remember it works on floating numbers. Okay, so for example, we can have fabs here, as you can see, fabs, and let us provide like a negative. I've not used negatives ever since I started this lesson. Let us try to use that one, and then we'll try to compile, then we'll try to run. As you can see, we get the 3.5. okay, that one. Okay, we get the 3.5, but not in negative. Okay, not negative. Let's try to remove that negative, and then we compile, and then we do that. As you can see, we get the same. Okay, so it gets us the absolute value of the floating number. Okay, so we have also another one which is called the ABS. Okay, ABS or abs, okay, ABS. Okay, and this one works for integers. Okay, and it is found in the std library. Okay, std library. Okay, .h. Okay, so we can include it like this one. We can use hashtag include std lib.h. okay, that library. Okay, so we can come here and then we use our abs like that. Okay, abs, and here we can come here and then we provide the integer. Okay, so here if we provide 10 like that, and we try to compile, then we do that, we get this one. Okay, we get 10.000, okay, like that, which is at 10. Okay, because here we are using floats. Okay, so let us go back to the previous one. Okay, this one, it is called the fabs. Okay, so let us use fabs like that, and then here let us have an integer like that. So let us try to compile, then we run it, runs successful. Okay, so we have another one which is called the hypotenuse function. Okay, and this one returns the square root. Okay, of the square of the summation of the square root of the base. Okay, and the square and not the square root and the square. Okay, the square of the base and even the square of the, should I say, the opposite. Okay, so let me show you something here. Let me show you here. So as you know, okay, the formula for finding the hypotenuse, okay, if you have ever worked with the trigonometry. Okay, so here we have, it is here hypot like that, hypot for hypotenuse. It is going to get us the hypotenuse. Okay, so here as you can see, so let us provide in 3 and 4. Okay, so 3 and 4, 3 is going to be the base, and 4 is going to be like the height. Okay, the height, or can call it the opposite. So if we do that here, I think we are going to get around, is it going to be 5? Yeah, 5. It's going to be 5. Okay, because here we get 3 squared, we get 9 plus the 16, we are going to get 25. Okay, we are going to get 25. Then 25, the square root of 25 is going to give us 5. Okay, so that is it about math functions in C. Okay, so play around with them, you can create good programs with math functions. Okay.